essentially by using tools from random matrix theory that are needed because you're sampling the manifold and you're adding noise, you can prove that the number of points that you need in such a ball for the estimate of the singular values and singular vectors to be accurate to be only linear in the intrinsic dimension of the manifold, not exponential anymore. One remark that I would like to make is that so small balls are not useful, medium balls are not useful. Large balls at this radius are useful. They really tell us geometric information of the manifold. But if I pick a radius which was even larger, that would also be not useful because I would start seeing parts of the manifold that were far away but have curved back, and they will be in a large ball. And then I would be detecting directions, such as the direction connecting this point to this point over here, but have nothing to do with the intrinsic dimension of the manifold. So there is an interval of radii which is useful. All the others are not. So this problem is truly multi-scale. So let me show a trivial example. Let me pick an n-dimensional sphere in 100 dimensions, and let me sample 1,000 points. The 0 there is for no noise. I'm going to change that in the next slide. So we have an n-dimensional sphere, and as a function of the radius, I'm going to pick a point and pick a ball of radius r and look at the singular values, and then I'm going to look at how they change as the radius increases. When the radius is small, I see 10 singular values which are large. The other 90 are down here and equal to 0, exactly, because my 9-dimensional sphere fits exactly in a 10-dimensional space. But as the R changes, I see that 9 singular values, the ones up here, behave very differently from the 10th one. These are the ones seeing that the sphere is 9-dimensional, and this is the 10th one seeing curvature. And then when the radius is too large, I'm looking at the sphere from far, far away. I can't tell whether it's a 9-dimensional sphere or a 10-dimensional ball. And all my singular values are equal, and I will be seeing a dimension of 10 rather than 9. So I think of these sort of as the tangent singular values, the curvature singular values. What happens, by the way, you might think that this example is completely trivial, it's just a 9-dimensional sphere. On the other hand, it's not completely trivial, I claim, because we have sampled 1,000 points. Is that a lot? Well, the sphere sits in R10, really, and in R10 there are 2 to the 10 orthants. 2 to the 10 is 1,000. So we have about a point per orthant. If we were in 2D, it would be like telling you that you have a 1-dimensional circle and I sample 2, 3 points on it, and I can tell you that it's 1D and it has 1 curvature. All right, so it's kind of crazy that one can see curvature with so few points. But what I think is even more surprising, or at least it was to me when I first ran these examples, is that you can tolerate a huge amount of noise. So what I'm going to do now is I'm going to add to each point noise, Gaussian noise, of standard deviation 0.1 in each dimension. How big is that noise? Well, if I call eta the noise, and I look at the expected length square of that noise, but expected length is 1. And in fact, I could take the square out, and also, so not only the expected length square is 1, but the expected length is essentially 1. But 1 is also the radius of the sphere. So I'm sampling 1,000 points on the sphere, and each of them gets moved in a random direction at distance 1. Okay, so the noise is as big as the object that you're looking at. If you do multiscale SVD, as a function of the radius, when the radius is small, so the range of the radius here is the same as in the previous picture. It extends a little bit farther to the right, but it starts at the same point. So now, for small radius, nobody's there. All the points have been thrown out of the manifold in higher dimensions by the noise. Then when R is about the size of a noise or a little bit more, you see a lot of singular values. These are all uninteresting. They're completely corrupted by noise. But then there is a range of radii where you see 9 singular values measuring the tangent space to the sphere, 1 singular value measuring curvature, and the other 90 seeing noise. And so this construction, even in the presence of large noise and not a lot of samples, certainly we're not cursed by the intrinsic dimension as much as one might worry, can detect the intrinsic dimension. So we use this tool, so we prove these statements mathematically, but then we use this tool to detect the intrinsic dimension of data sets. And we tried this on tens of data sets and saw that the intrinsic dimension is typically very low, between 1 and 5 or maybe 10. So I'm not going to show you those results, but let me show you for the blobs. If you look at the picture of blobs and you run multiscale SVD, so you pick one blob and when you start looking around and you do SVD, you see two singular values which grow linearly. Those are the ones measuring the tangent directions, and they say that the manifold is 2D. And then there are others measuring curvature, there are 3 of them, and then there are others measuring higher order curvatures at larger and larger scales. But this detects that the dimension of the set is 2. I'm sorry, this doesn't show really nicely, but there are 2 almost perfectly linear curves here, corresponding to the intrinsic dimension, 3 curvatures here, and then more and more curvatures coming up. There is no noise here, but even with noise, this would be robust. So I'm not going to show you other data sets except the ones for molecular dynamics, where people had no idea about how to go and measure the intrinsic dimension and how to use that. So let me tell you just a little bit about how the data is generated, or at least a model on how data is generated. So X is a molecular configuration, so it's a long vector of dimension 3n, where n is the number of atoms. And so it contains the x, y, z coordinates of all the atoms. And one way of in which one can approximate molecular dynamics data is by saying that the following stochastic differential equation is being simulated. So this is saying that the velocity of my configuration vector is equal to 2 components, one deterministic, which is the gradient of a potential in the state space of the molecule. This is going to push the molecule towards configurations of lower energy. Plus W dot, which is notation for random noise, Brownian motion, possibly colored. So this is the stochastic component. So at every time step, the velocity is equal to a drift coming from the gradient of U and a random kick in the direction. The random kicks, usually you can think of them physically as saying, well, the molecule is in a solution, there are many water molecules kicking the molecule of interest, while the effect of all those kicks from water or solvent molecules is some noise. Okay, typically colored. And so let me pick a very small molecule. This is a molecule of Alanine dipeptide. It has a 36-dimensional state space. There are 12 atoms, 3 coordinates each. And physical chemists know, they have good reasons for knowing that 2 angles are really crucial to the behavior of this molecule. These 2 dihedral angles, phi and psi. And so what they typically do, they draw a plane, phi psi, and then they put a color in the plane that corresponds to how often the molecule is in a configuration with a given value of phi and psi. Blue means the molecule is often in this configuration. Red means it's very, very unlikely to see a molecule with a configuration which has these angles phi and psi at these positions. So you get a landscape, and you can think that your molecule sits at a high probability region for a long time. These are low energy, high probability configurations. And then every now and then, with the random kicks, it transitions to another low configuration energy. Maybe going through a mountain pass of energy, like over here, or maybe between here and here. So you can go and now measure, these trajectories of the molecules in 36 dimensions. How low dimensional are they really? So you can pick a transition region over here. This is a mountain pass. And you can look at the trajectories. And so you pick this point, you run multiscale SVD, and you see that near the transition region, the intrinsic dimension is 1, or maybe 2. So there are very few ways in which the molecule can go from here to here through this transition path, because that transition region is essentially 1 or 2 dimensional. So why are we running the molecule using 36 equations? We should only need 2 equations in the right coordinate system. If you go near a minimum of the potential energy, where the molecule spends a lot of time, and you look at the intrinsic dimension, that's kind of higher. Maybe it's 2, maybe it's 5, depending on how you read these plots. But there are many directions which probably do not matter. And so the dimension is higher. It changes from location to location. These plots don't look as nice as the ones for a manifold. These things are not manifold-like. But nevertheless, this multiscale SVD is suggesting that the intrinsic dimensionality is in fact pretty low, much lower than the dimension of the state space. And we've verified this on larger and larger molecules and so on. And so we can use this information now for actually trying to discover pictures like this. If I have a complicated molecule and I don't know which coordinates are important, we're going to construct new sets of coordinates which are important. So let me describe how we do that. So how we find coordinates for data sets. Principal component analysis was finding coordinates when the data was on a plane. I want to find coordinates when the data is on a manifold-like object. So how do we do that? Well, the problem is sometimes called manifold learning. By different people mean different things by manifold learning. And so the problem is the following. So you have a domain in Rk, that's your parameter space, like the position of a blob in the case of the blobs, or the angles in the case of the molecule. And then you have, so K is the intrinsic dimension of the data. And then you have a map phi from the parameter space to high dimensions. And the data is obtained by picking points in the low dimensional domain omega and mapping them to high dimensions. Like the blob, the parameter space was a 2D square, and the map was mapping every point in the 2D square into a 4,000 dimensional vector, which is an image of a Gaussian center at that point. Now, given samples in high dimensions, we would like to learn the map phi, or its inverse. So we would like to start from high dimensional data and learn the low dimensional parameter space and the connection between low dimensions and high dimensions. And so in 2001, Tenenbaum, De Silva, and Langford published, I think on Nature or Science or PNAS, a paper called ISOMAP that tries to do this. And it does succeed in doing this under certain assumptions about both the domain and the map phi. Notably the fact that phi needs to be an isometry and omega needs to be convex. And they show that if you get, as you get more and more samples, you can learn this map phi. And then Dono and Grimes refined this to the case where phi is still an isometry and omega is non-convex, so it might have holes. And then many other work followed, among which the one on diffusion method I'm going to discuss now. And then after that, there has been even more work. So now there are lots and lots of papers that try to tackle this problem. So the idea behind the construction of diffusion maps, and in fact many other algorithms, they are sort of part of the construction is similar, is the following. You start from data, and then you want to construct a network or a graph on that data set. The way you do this is the following. So you assume that somebody gave you a similarity between data points. For example, a function such as e to the minus distance between the points squared divided by sigma. This function is essentially 1 when points are close and 0 when points are far. And then you're going to construct a graph where the vertices are the points and the edges connect points, and the edges are weighted by the similarity function. So you get a weighted graph, data points are vertices, and they are connected in this network. Note that from this point onwards, if we're only going to talk about the network, this network is sort of intrinsic. The ambient dimension is gone. It appeared here when we construct the network. This distance was the distance in high dimensions. But once the network is constructed, the network is intrinsic. It sort of lives on the manifold where the data is. And so all the objects that are constructed on that network are going to be somehow intrinsic they are going to depend only on the intrinsic dimensionality of the data. And the most natural object on a graph, on a weighted graph, I claim, is the random walk. How do you do a random walk on a weighted graph? I need to tell you what's the probability of jumping from vertex I to vertex j. Well, if vertex I and vertex j are connected and the weight of the edge, i.e. the similarity, was large, I want that edge to have a large probability of being picked. And so I would like my random walk to be proportional to my similarity w. I can't do that because w is not stochastic, so I wouldn't, the sum of probabilities jumping from xi to xj wouldn't sum to 1 when I sum over xj's. So you just normalize your similarity matrix by pre-multiplying by this matrix D, or its inverse rather, which is a diagonal matrix whose ith entry is the sum of the weights connected to vertex I. So now P is a stochastic matrix, and you can do these random walks on the graph. You can talk about eigenvalues and eigenvectors of P. The eigenvalues, turns out, start from 1 and they decrease. And there are corresponding eigenvectors that I'm going to call phi. And we're going to consider the following map. This is going to be a map from the graph to Rm. So we're going to embed the data set that was in ID, was converted to a graph, and we're going to embed that in low dimensions by mapping each data point, or each vertex of the graph, to the value of the first m eigenvectors evaluated at that point. So each eigenvector is an n vector. We had n data points. The matrix W was n by n, P was n by n. This is an n vector, and so each of these eigenvectors can be evaluated at points. And this map might seem odd. You know, you have eigenvectors evaluated at points. Well, let's see what it does in the case of blobs. You have these blobs. You connect each of these images to the images which are most similar to it, and you construct this weighted graph. And then you use the first two eigenvectors of the random walk to embed, and you get a square. Well, the square was the parameter space. The parameter space was the center of the blob, which was picked on the square. So this map recovers the square in this very simple case. And it does that in many, many, many cases. So let me show you. So since I don't have a lot of time, I had a little demo which I'm going to skip. But I always have a lot of fun with this demo. But let me show you what you get, for example, for a piece of music. This is the same piece of music that we had at the very beginning. I mapped it to a data set which was in about 100,000 dimensions by picking short time windows and embed it in low dimensions. Well, the data is essentially 1D. After all, it's a time series. But there are parts of the music that almost repeat themselves with small variations. And that's where this region gets crowded. So the music returns on itself in certain regions. You can do it for many different data sets. So here is a data set of text documents. Each text document can be mapped to a high dimension